Behind just about every major industrial process, think refining fuel, generating power, there are these powerful, hidden muscles doing all the heavy lifting. They're called actuators, and they are pretty much the unseen heroes of modern engineering. So let's pull back the curtain and see how they actually work. Okay, so just imagine for a second. You need to precisely control the flow of thousands of gallons of fluid. Maybe it's water for a power plant or fuel for a refinery. You can't just walk over and, turn a little handle. The forces we're talking about are absolutely immense, and the stakes incredibly high. So how do you even do that? Yeah, in a setup like this, opening or closing just one of those valves, well, it takes a level of force, precision, and reliability it's completely beyond what any person can do. This is exactly where you need some serious industrial strength muscle. And that industrial muscle we keep talking about, it has a name, the actuator. This is the component that takes a command, an electrical signal, and translates it into pure physical force. It's what moves the bones of the industrial world to get the real work done. So, to put it simply, an actuator is just a power-operated device that hooks up to a valve and gives it the oomph it needs to move. Now, engineers have specific names for this force. They call it thrust when it's straight-line motion, like pushing, and they call it torque when it's a twisting motion. It sounds pretty simple on the surface, right? But believe me, the technology behind it is actually incredibly sophisticated. And this illustrates the whole setup perfectly. If you think of the actuator up top as the muscle, that's what provides the power, then the stem is like the bone, transferring all that force down. And finally, the plug at the very bottom, that's the hand, the part that physically moves into place to either block the flow or let it through. So what exactly does this industrial muscle need to be able to do? Well, it really has 4 critical jobs. First, it has to be strong enough to push against all that fluid pressure. Second, it has to be precise enough to hold a very specific position when it's told to. Third, it absolutely has to be reliable, with a built-in failsafe. We'll get to that. And finally, it has to operate at exactly the right speed for the task. Now, actuators can be powered by a few different things, but we're going to start with the most common type out there, pneumatic actuators. And what gives them their power? Well, it's a surprisingly simple, everyday source you might not expect. That's right, it's just air. Pressurized air. By controlling the pressure of that compressed air, these devices can generate an incredible amount of force and position a valve with, pinpoint accuracy. It's a simple, super reliable, and really cost-effective solution, which is why you see it used all over the world. Okay, so these pneumatic actuators generally come in 2 main flavors. First, you've got the piston actuator, which you see in this diagram. It uses a solid disc that moves inside a cylinder. And then you have the diaphragm actuator, which uses a flexible membrane instead. Both use air pressure to do the work, but how they do it on the inside is just a little bit different. So what's the difference in the real world? Well, you can think of piston actuators as the heavy lifters. They can handle much higher pressures and they can move a lot faster. Diaphragm actuators, on the other hand, are often simpler. They typically use air on one side and a spring on the other to provide the opposing force. They're the reliable workhorses you find in just countless industrial applications. Right, so how does a computer, maybe miles away in a control room, tell this physical thing what to do? It's a really clever 2-step process. First, the main controller sends out this tiny, standardized electrical signal. Then, a little device called an IP converter acts like a translator. It takes that electrical signal and converts it into a proportional amount of air pressure. So a low signal means low pressure, a high signal means high pressure. It's just a really elegant way to turn pure data into raw physical force. Okay, but this is where the design gets really ingenious. What happens if that control signal is lost? What if the power goes out or a wire gets cut? In a high-stakes industrial plant, leaving a critical valve stuck in the wrong position, well, that could be an absolute disaster. See, under normal operation, that signal is constantly telling the valve what to do. But if that signal suddenly disappears, the system doesn't just freeze up. No way. It's actually designed to automatically move to a preset, safe position, all on its own. The moment that signal is cut, the pure mechanics of the actuator take over. The loss of air pressure lets this powerful internal spring do its job, forcing the valve into its designated fail-safe state. There's no computer involved, no electricity needed at this point. It's just pure, reliable, mechanical safety. And that safe position can be one of two things. You can have a fail-to-open valve. This means if the signal is lost, a spring forces the valve open. You'd use this for, say, a cooling water line, where you absolutely need flow in an emergency. The other option is a fail-to-close valve. It does the exact opposite. It slams shut. This is perfect for something like a fuel line, where an uncontrolled flow would be, catastrophic. So, while these pneumatic actuators are super common, air isn't the only game in town. Engineers can also turn to two other major players, hydraulic actuators and electric ones. And this table breaks it down pretty nicely. Pneumatic, powered by air, is low-cost, simple, and fast. Hydraulic, which uses pressurized fluid like oil, gives you the most brute force. We're talking serious power for the biggest jobs. And then you have electric. It's super precise and the cabling is easy, but it tends to be slower, and this is a big one. It usually doesn't have that built-in mechanical failsafe we just spent all that time talking about. Okay, so with all these different options, how on earth does an engineer pick the right one? Well, as you can imagine, it's a really critical decision, and it all comes down to the specific job at hand. Because ultimately, there's no single best actuator. It just doesn't exist. The pneumatic system that's absolutely perfect for one application might be completely wrong for another. When you're talking about industrial design, context is everything. Engineers have to weigh a whole bunch of factors. What is this valve actually doing? What power source do we have available? Is there compressed air or high-pressure oil? How fast does this thing need to move? How much force do we need? What kind of valve is it? And, of course, what's the budget? The final choice is always a very careful balancing act between all of these things. Really, the actuator is a perfect example of one of these critical systems that are just hidden in plain sight. And it kind of makes you wonder, right? What other invisible engineering marvels are out there quietly keeping our entire world in motion? Thanks for digging into it with us.